Hi students, this is Alex here. In this problem they have given f of z, which is u plus iv is a regular function of z in a domain D, and we have to prove del square log of mod f of z is equal to 0, and there is a condition if f of z into f dash of z is not equal to 0 in D. Now let's start with f of z, which is u plus iv, and mod f of z will be root of u square plus v square, and we have log of mod f of z in our question. So let's take log for this, log of root u square plus v square, and this can be written as log of u square plus v square whole power half. Using log rule, we can bring this half here, so half log of u square plus v square. Now coming to the left hand side, we have del square log of mod f of z. So let's take LHS. We have del square log mod f of z. So del square half log of u square plus v square. Now we are going to use the del square operator. Del square is dou square by dou x square plus dou square by dou y square. Now this is dou square by dou x square plus dou square by dou y square whole thing, and we have half of log u square plus v square. Now this entire term I am going to take it individually for each partial derivative, that is dou square by dou x square half log u square plus v square, again plus dou square by dou y square half log u square plus v square. Now this half is a constant which can be taken out, and the second derivative we are going to split into two parts, dou by dou x of log u square plus v square, first term. In the same way, half is taken out, and we are going to split this into dou by dou y of log of u square plus v square. Now this first part we are going to continue the partial derivative. So outside we have half, and also we have dou by dou x. Derivative of log is 1 by, so 1 by u square plus v square. Then by chain rule we have to find derivative of u square plus v square. U square derivative is 2u, and with respect to x, u derivative is ux plus 2v into vx. So we find the derivative of u square plus v square with respect to x using the chain rule. The first term is completed. In the same way, plus second term, which is half dou by dou y and 1 by u square plus v square and 2u uy plus 2v vy. So here everything is partial derivative with respect to y. Now from the numerator part we find 2 is common, which can be taken out here. The same way for the other term also. So 2, and already there is 1 by 2 outside. Then we have dou by dou x of, we have ux plus vx whole division u square plus v square. In the same way, plus 2 by 2, then we have dou by dou y of uy plus vy whole division u square plus v square. And outside we can cancel these numbers. Now we are going to do partial derivative of this entire term, but this entire term is in the quotient form, that is u by v form. When we have u by v, so we follow the quotient rule. Let's write the quotient rule here. When you have numerator and denominator form, u dash v minus u v dash by v square. Now I'm going to apply this. So the first term, this entire numerator is considered as u and the denominator is considered as v. So u dash, it means ux plus vx whole dash, but the first part is with respect to x. Then v is written as it is, u square plus v square minus u, again ux plus vx, and v dash is u square plus v square whole dash. Then whole division, we have v square, that is nothing but the denominator square, u square plus v square whole square. Now plus, the same thing you have to do for the second term, which is uy plus vy whole dash u square plus v square minus uy plus vy into u square plus v square whole dash whole division u square plus v square whole square. Now the first part is everything partial derivative with respect to x, second part is partial derivative with respect to y, and in both the terms we find a common denominator, so that we write separately as 1 by u square plus v square whole square. Now open a big bracket. Now from each term we have to continue. This we have a whole dash, it means partial derivative of this. Again there is a product rule for this. So u derivative is ux, and second term we keep as it is, plus first term we keep as it is, and second term derivative is uxx. In the same way vx, so v derivative is vx, and second term we keep as it is, plus first term we keep as it is, and second term derivative is vxx derivative vx derivative vxx. This whole thing we have multiplied with u square plus v square. Then we have a minus sign. The same thing I have to continue for the second term, and in the second term the first term is written as it is, and here the derivative of u square is 2ux plus derivative of v square is 2vx. Then plus, I have to continue for the second term, but now this is with respect to y. So again when I follow the product rule for this, u derivative is uy, and the second term uy is written as it is, plus first term is written as it is, uy derivative is uyy. In the same way for the second, vy into vy plus v into vyy this whole thing is multiplied with u square plus v square, and there is a minus sign, and again uy plus vy into 2u uy. This derivative with respect to y, u square derivative is 2u uy plus v square derivative is 2v vy. So we completed the derivatives, and now we have to simplify everything. While simplifying, let's group the first term and third term together. So this first term is having all these things as a product, and here's third term is having all these things as a product. So I'm going to take the common terms first. So 1 by u square plus v square whole square, open a bracket. Now u square plus v square present in both the term, when that is taken common, we have to add all these things. This is ux whole square, this is vx whole square, this is uy whole square, this is vy whole square. So everything I am going to write it together here. This is ux whole square plus, and we have uxx plus vx whole square plus vxx plus uy whole square plus uyy plus vy whole square plus vyy. Close the bracket. Then two minus signs are there. We shall take the minus, and in these two terms we find that after taking this 2 common, this is ux plus vvx, and we have the same thing here, ux plus vvx. So I write 2 common, then remaining is ux plus vy whole square, because we have 2 times. Same thing here also. So minus 2 uy plus vy, sorry, this is x actually. This is x here. So vx whole square, uy plus vvy whole square. And this equation, I mean this function, satisfies the Laplace equation. That is, Laplace equation is dou square by dou x square, that is u, plus dou square u by dou y square. This will become 0. It is nothing but actually uxx plus uyy equal to 0. In the same way, vxx plus vyy also 0. So now I am going to take u common from these two and v common from these two, so that I can use these two expressions, so that I can reduce the term. So outside we have 1 by u square plus v square whole square, open bracket. We have u square plus v square, and first let's take u common. So it is uxx plus uyy, and again plus v common, this bracket close, vxx plus vyy. Apart from that, we also have ux whole square plus vx whole square, and we can use CR equation and change these two with respect to x. That is, our CR equation is ux equal to vy and uy equal to minus vx. So how we are going to replace it here is, let's check here. So we have written ux square vx square, then uy is written as minus vx, so minus vx whole square, and vy is ux whole square. When we square anyway, it will become plus. Then bracket close, and again we have minus 2 ux plus vx whole square minus 2 u, in place of uy let's use minus vx, plus v, in place of vy let's use ux here. So everything we changed in terms of with respect to partial derivative with respect to x. Now anyway, these two terms becomes 0, and after that let's write the remaining, that is 1 by u square plus v square whole square. Then outside we have u square plus v square. After this becomes 0, and we can add these two terms. So 2ux whole square plus 2vx whole square. When I square, this becomes positive, and we can add these two as 2 times. Then apart from this, we have minus 2. Let's write the other terms as it is now. ux plus vx whole square minus, and there is a 2 outside, and there is a minus sign, so let's write this one first. vux minus uvx, bracket close, and even there is a square for this. So here there is a square, and in the previous step we have written. Fine. Now every term has, by taking this 2 common, we get 2 in the first term, and even there is a 2 here. So let's take 2 common. So 2 by u square plus v square. After this we have u square plus v square into ux square plus vx square, then minus ux plus vx whole square minus vux minus uvx whole square. After this, it is purely expansion. So outside we have 2 by u square plus v square, and now we multiply each term with this. So we get 4 terms: u square ux square plus u square vx square plus v square ux square plus v square vx square. And this also we are going to expand, and there's a minus sign common, so I am going to take minus for everything. Minus u square ux square, then minus 2u ux v vx, and minus v square vx square. Again there is a minus, so minus v square ux square, then minus 2ab term, but already there is a minus outside, so plus 2v ux u vx, and last term is again minus. I have taken the minus sign inside, so u square vx square. So we completed the expansion. Let's see anything gets cancelled. Actually minus 2u ux v vx, even here u ux v vx, so plus and minus term we can cancel. Similarly u square ux square minus u square ux square, and v square vx square minus v square vx square, we can cancel. Then we have u square vx square, even this we can cancel, u square vx square minus u square vx square. Then finally one more term, which is v square ux square minus v square, everything gets cancelled, so finally it is 0. So 2 by u square plus v square into 0, that gives 0, which is nothing but the right hand side. So we took the left hand side of the given expression and we proved 0, which is the right hand side of the given expression.